Hello everyone, welcome to what will be pre-lecture number 35. We're going to talk about reaction mechanisms and catalysis. So to start with, I want to bring up some things that we've seen before, but maybe not in this context, and bring in this kind of new quantity of activation energy. And so the way I want to introduce this is with something called the Arrhenius equation, which is shown right here, which is K, which is our rate constant that we've been working with for the past week or two, A that we talked about last class, which is our frequency factor, E being the basically exponential function to the negative. This is our activation energy divided by RT, and R, of course, is our ideal gas constant, T is our temperature in Kelvin. So this can be a very handy equation in that if we perform the measurement of the rate of a chemical reaction at multiple temperatures, then we can actually take the natural log of both sides of this equation and end up with something that is a y equals mx plus b type relationship, where if we graph the natural log of our rate constant versus 1 over the temperature in Kelvin, then we should be able to get a straight line, and the slope of that line, our m, is the negative activation energy over R, which is our ideal gas constant. And so that can be super handy. We're going to practice that in class. And it's actually, as long as we have multiple rates and temperatures, we could actually use a two-point form of that equation as well, where if we have two rates, two temperatures, we should also be able to solve for the activation energy. So two ways we can do this. In this first equation, this is also a way that you would figure out your orientation factor, which is something that is, of course, not obvious just from looking at chemical species. Okay? So that is one way we're going to look at activation energy. We're also going to talk about reaction mechanisms today. And so many times chemical reactions occur in a stepwise fashion, and that means we have two or more distinct steps that take place in a predictable sequence. And we tend to call that a reaction mechanism or reaction path. And that will give us details about the step-by-step process and help us understand it better. And I will say, for those of you going on to organic chemistry, reaction mechanisms are incredibly important in organic chemistry and really all of the rest of chemistry once you get past a Gen Chem level. Okay? So an example, a relatively simple one, is the decomposition of ozone, that we could break up into two steps. So the first step would be O3 gas, which is ozone, dissociating into O2, and then just an oxygen atom. That oxygen atom can react with another equivalent of ozone, and then we end up with overall, or we end up with 2 O2 from that reaction. And so that is our overall reaction, or our multiple step reaction, but our overall reaction, we would basically sum up what is in our reactants, what is in our products. So we end up with 2 moles of ozone on our reactant side. That's why that's here. We end up with 3 moles of O2 on our product side. That is why that is there. And then we end up with an intermediate. So an intermediate is something that is produced as a product in earlier step and then consumed as a reactant in a later step. And so in this example, that is just this O atom here that is produced in our first step, consumed in our second. And so we don't put that in our overall reaction. Okay. Within this, we would then call those multiple steps elementary steps, in that we are only doing one thing at a time. And so we can have many, many steps in a reaction path, but typically pretty common, I would say 2 to 4 to 5 is pretty common. And so here's another example. We'll go through this one in class where we have 2 moles of NO that dimerizes. That dimer then can react with H2 to make N2O, H2O. That N2O can react with another equivalent of H2 and make N2 and another equivalent of water. And so something I'm going to ask you in class, if you want to start thinking about it now, is what is the overall reaction, what intermediates occur during the elementary steps, and to write a rate law for our second step. Okay? And so within that, I want to discuss a little bit more about mechanisms here and some of the vocabulary we use around them. Molecularity is a common term to describe the number of molecules involved in our reaction. So if something is unimolecular, we have one reactant, it goes to products. Our rate law would be rate is equal to K times A, right? And that should be fairly straightforward based on what we've talked about already. For bimolecular things, we can either have two of the same molecule go to products or two different molecules form products, and their respective rate laws would be written like this, right? Where we either square if we have a single chemical or multiply, get the product of our two reactants. And it goes on, termolecular, we have three, et cetera. Generally, you don't have more than a termolecular elementary step because just the sheer probability of three atoms or molecules running into each other at the same time is relatively low. And so if you go beyond that, things get incredibly low probability to the point where reactions don't really seem to happen, okay? So within this, within our elementary steps, if we have multiple steps in our reaction, we're going to need to determine which one of those steps is the slowest. And that will be what determines the overall rate of the reaction, thus its name, the rate limiting or rate determining step. So a nice analogy you might be able to think of, say we have a 4-lane highway and it closes down all but one lane due to an accident or construction. And that creates a bottleneck where only one car could be able to get through at a time. And so whatever our slowest step is, that is going to limit the rest of the chemical reaction, even if the rest are very fast, okay? So if we think about this reaction here, where we have NO2 plus CO makes CO2 and NO, at temperatures above 225 degrees, we can basically experimentally determine a rate law where K is equal to NO2 times CO, which is essentially what we just have there. And below that temperature, our rate law is only dependent on NO squared. K equals, and this should be, sorry for the typo there, NO2 squared. And what that tells us is basically we undergo a change in our rate law. And so in the first reaction, we have just our overall reaction. But if we break these down into their elementary steps, and this is not necessarily something you would know how to do, I would have to give you how to break them down into their elementary steps. But we could see that we have two NO2s making NO3 and NO, which is our slow step. And then we generate this intermediate NO3, that is what reacts with CO to make our products, our CO2 and our NO. Or another equivalent of NO2, and that kind of cycles back in. So basically that rate determining step would be this first one here, okay? We also can talk about reaction mechanisms in terms of catalysts. And so catalysts are something you may have seen in a biology class before or heard of for other reasons. And we define a catalyst as something that increases the rate of a reaction without being consumed by it. And so this is ultimately accomplished by lowering the activation energy, and it is oftentimes breaking one more difficult step into multiple easier steps. And so if we look at this example here, if our initial uncatalyzed reaction is this red trace, we see we have a very high activation energy. Based on what we talked about last class, we should know that the primary thing that limits the rate of a reaction is the activation energy barrier. And if we have a catalyst that lowers our activation energy and just so happens to break this reaction into multiple steps, then overall we get a much faster reaction, okay? So it does not necessarily involve a different number of steps. However, it does often provide a different mechanism, and if nothing else, we have another molecular species in the form of a catalyst that is present. A key point that I want to emphasize here is that catalysts do not change the amount of product formed, only how fast the reaction goes, okay? So because it is easier to go from left to right in this diagram, that actually means it is also easier to go from right to left. So we increase the rate of the forward reaction, but also the reverse reaction, if we're thinking about this in terms of equilibrium. So the overall percent yield, we could say, of the reaction is still going to be determined by thermodynamics, related to essentially the favorability of our reaction based on things like Gibbs free energy and our entropy and enthalpy. Okay. So just some key points to know here. If we make the figure that we saw last class a little bit more complex, we have our uncatalyzed reaction at the top of any of these hills where these stars are. That is where we have transition states. When we're in a valley here, in a multiple step reaction, those are what we would represent as our intermediates, okay? And then of course, whether or not a reaction is endothermic, exothermic, exergonic, endergonic, that is still determined by thermodynamics, and it is unaffected by our catalyzed reaction, okay? So some examples where you might have seen this, enzymes are essentially homogeneous catalysts that perform biological reactions. And so you have literally millions of these reactions happening in you right now, keeping you alive. So say thank you to your enzymes for doing that. Kind of a classic example that's shown here is glucose 6-phosphate dehydrogenase. And this is the rate determining enzyme in cells that produce NADPH. And so this is the catalyzing reaction here. And so that is something that you can bring to your biology class and say, I recognize this is an enzyme, that is a catalyst, that is rate determining in the regeneration of our cofactor NADPH, right? We also have heterogeneous catalysts. So heterogeneous catalysts are in different phases than the reactants or products that they're catalyzing a reaction for. So kind of a classic example would be a surface and then a liquid or gas passing over that surface. So in this example, we have a nickel surface that H2 can bind to, or what we would say adsorb to. And so our H2 actually breaks apart to make H atoms bound to that nickel. We can get this molecule called ethylene here, and it can actually eat up those hydrogen atoms and form ethane. So we have a net transfer of hydrogen allowed by this catalyst here. One that you probably have used in the last week if you've driven is a catalytic converter in your car. So we get emissions from basically the engine. They go through this catalytic converter that contains precious metals that is heated up, and it essentially deals with a lot of our worst emissions, converting them just to CO2 and water on the way out, or sometimes occasionally N2 as well if we have nitrogen in our gasoline. Okay, and so if you've driven today, congrats, you have done some catalysis already. Anyway, that'll be it for our pre-lecture video. If you have any questions, please do let me know. Otherwise, I hope you have a great day.